this lecture, we will discuss generalizations of RMA. So, when the task deadline and periods are not the same, when DI is not equal to PI, specifically when the deadline is less than PI, so we can't use the same RMA formulation. RMA will not be the most optimal scheduling algorithm, as we have seen for cases where DI is equal to PI. So, in this case, the deadline monotonic algorithm, which is also a static scheduling algorithm, but it actually the formula takes the deadline into account. This and then the priorities are assigned based on the task deadlines. So the task deadline is one of the inputs to the formula. This is the most optimal. So we'll not discuss the details of DMA, but at least we'll motivate the need for DMA. So when do RMA and DMA produce identical schedules? When the deadline is same as the period. That's obvious. But for arbitrary relative deadlines, DMA may produce a feasible schedule, specifically when RMA fails, right? On the other hand, given that DMA is the most optimal in that space, whenever DMA fails, RMA will also fail. So you will find a pointer to DMA on the website of the course. So let us now look at some of the other overheads of RMA. So these are things that we typically don't consider, but this is something that should be considered in a practical implementation. The first is the overhead of context switching. So far, we have neglected the overhead of context switching, but the idea is that whenever one task is running and then another task starts, there is a small gap. So basically, so this small gap is basically because this is the time that the operating system will take or the runtime will take to change the task. So it basically preempts the currently running task which has a lower priority. And of course, if the task that was currently running had a higher priority to begin with, it will not preempt any other task. So in the worst case, what will happen is that each task will incur at most two context switches. For the first context switch is when it started running, if it preempted some other task, and the next context switch would be when it will finish, right? So that will be the other context switch, right? So at most two context switches every task will incur, and it may not incur those, right? If let's say it's the only task that's running, but again, this is the worst case. So let the context switching time be constant and let it be equal to c milliseconds. So effectively, what is happening is that the execution task time of each task is increasing to ei plus 2c, the execution time plus 2 times c. So let us assume three periodic tasks with the EPD values as these, and assume the context switching time to be 1 millisecond, and now see if it is schedulable or not under RMA. So in this case, what we do is we consider E1 plus 2C for each, and then we apply the Lehowski's criterion, the Liu and Lehowski's criterion. So note that 10 becomes 12, 25 becomes 27, and 50 becomes 52. So with these, we nicely apply the Lehowski's criterion, and then we see that the criteria are satisfied. As a result, the task set is schedulable even when we consider the effect of context switches. So a practice problem here, see if these set of tasks are schedulable or not, all right, within RMA, right, within the scope of RMA. And of course, assume that the overhead of a context switch is 1 millisecond. So essentially, it will become plus 2. Each one of them will become plus 2. So let us now look at handling critical tasks with very long periods. So many a time, if they have very long periods, they may not be schedulable. So we have looked at a bunch of tests, Liu Leyland test, Lehowski's test, and so on. So the main idea is that if the periods are particularly very long, then we may have a reasonably high difficulty of scheduling something, right? Another thing is that the priority of the task could be very low. Given the fact that its priority would would be low, its response times will be very high. Hence, to make RMA schedulable, what we should do is basically divide a period into several subtasks, where, of course, if the task is dividable, in the sense, if the length of the task is E, and we divide it into several parts, and each one of them will have a shorter period. So, in this sense, each one of the parts will at least have some degree of guaranteed completion, and we may see a better response time. But of course, this heavily depends on the nature of the task. So, this is known as period transformation, and a solution has been proposed by Shah and Rajkumar. So, the idea here is to divide a large critical task into many smaller subtasks. So, let Ti be a critical task that is split into k subtasks. Each one of them will have execution time ei by k, and the deadline also will reduce to di by k. So, at a conceptual level, we need to do it virtually. Of course, they may not be equal parts, but of course, and the task, of course, also remains the same in the sense that we don't want to physically change the task. So, in some cases, we might want to replace the task by different ones, or all that we can do is that we can take the same task and like virtually split it into k parts. In the first k interval, we execute 1 by kth. In the second interval, we execute the next 1 by k to 2 by k portion, and so on. So, the example of period transformation would be, for example, these two tasks. So, let's assume T2 is a critical task whose deadline is 30 milliseconds as opposed to T1 whose deadline is 20 milliseconds. So, even under transient overloading, we don't want T2 to miss its deadline. So, what we can do is we can create two subtasks, each with E2 by 2 or 8 by 2 4 millisecond work, and then have a shorter period and a shorter deadline also set at 15 milliseconds. So, period transformation in this sense can improve the schedulability. And as I said, it's possible that the first half of a task may be more critical from a response standpoint. Something similar to what we have, the way we have top halves and bottom halves and interrupt handlers. So then, of course, the key point will be that will have other connotations. But at least from a schedulability angle, it will become slightly easier. We should never have lopsided tasks. Some tasks being very small, some being very large. Because the one that is very large will always execute after the small task is done, and it will get frequently interrupted. So, impact on schedulability needs to be understood, right? And up till now, our discussions have assumed that there are no dependencies between the tasks. However, in practical situations, this will be far from the truth. So, existing scheduling techniques will have to be suitably modified to ensure that dependencies can also be taken into account. So, what we can do is that we can follow this table driven algorithm, is that we can arrange the tasks in increasing order of their deadlines. Right, so basically the first task over here, let's say T1 and then T2 and so on. So they're arranged in increasing order of their deadlines. So we'll scan the list from the rightmost end, which is this end, which means we'll start from the task which has its deadline at the end, right? The largest deadline. So then what we will do is that we will find a yet to be scheduled task whose all successors have been scheduled, and we'll schedule it as late as possible, right? So we will essentially start from the opposite end, right? And so basically any predecessor has to be scheduled before its successor. So since we are starting from the other end, that's fine. So normally what people do is that they start from T1, start from the earliest task, schedule the task, then look at its successors and its successors and so on. But in this case, we are walking backwards, right? So we will see one advantage with it, which is not there with the previous approach. So then what we do is we take every task and try to schedule it as late as possible. This is the key idea. This is the crux of the idea. that whatever slack is there, we keep it towards the beginning and we just keep on scheduling them as late as possible. As long as there are tasks to be scheduled, we keep doing that. So we'll of course come with a feasible schedule where of course you will see a fair amount of voids, empty spaces at the beginning and gradually more compaction towards the end. So we move all the tasks forward, right? So essentially what we are doing is we have moved them forward as much as possible, right? Forward in the time axis. And then after doing all of it, after like creating a feasible schedule, our aim would be to reduce the worst case execution time of the full series of tasks or the full set of tasks. So again, we'll move them backwards in the sense that we will just take all of them and as far as possible just push them this way. But of course, no task can be pushed to a point which is before its arrival time. So then what will happen is that the final schedule will look like this, where of course again there will be some compaction towards the beginning and gradually there will be open spaces towards the end, right? So basically what do? We start from the end, we create a feasible schedule keeping dependencies in mind, and after getting a feasible schedule we just push everything to the beginning, right, such that the response time is minimized. So what we can do is that, let's say if we have a set of real-time tasks like this, we can determine a feasible schedule using our logic, and this is the set of dependencies. So as per our logic between T4 and T5, you will see that T4 has the largest deadline. So we will schedule T4 first and then T5, and then between them we'll choose the deadlines, and then we will do what we did. So we'll arrange them in ascending order of task deadlines, which is T1, T3, T2, T5, and T4. We will schedule the task as late as possible without violating any precedence constraints. So as I had said, T4 will be scheduled at the end, then T5, then T2, T3, and T1. Then we will move tasks as early as possible. After doing this, we will shift all of them in this direction, which is this way, without altering the schedule, right? So then we will have a schedule like this where the schedule as such is not altered, and we still have a feasible arrangement of tasks which minimizes the response time to a large extent. We are not making any optimality claims here. Few more things can be done. We can extend event-based schedulers. So here now we have sort of gone out of the RMA domain. We are again, so we are kind of trying to generalize things. So the question is, how do you handle precedence constraints? So the key point or the key idea always is not to enable a task, right? If you are going purely event driven, and even if we are doing RMA or EDF, doesn't matter. The general principle is that if all the tasks are not known, which they may not be. So in the case of RMA or EDF, we are not really guaranteeing that we know every task at the beginning, even though the previous table driven approach, which is again a clock driven approach that assumes that we know we know about all the tasks, but assume that we don't know, but we can still keep this in mind that as long as the task predecessors are not done, we don't enable it for execution. And the moment that, let's say, the predecessors are done, we check the queue of waiting tasks to be enabled, right? And then based on whatever is our criteria, static or dynamic, we do the scheduling, right? So with precedence constraints, we can either adopt a table driven approach like this, or we can adopt an event driven approach where we basically observe precedence relationships and the rest more or less remains the same. So the basic idea, there's also another idea we can do. So in this case, this is more like taking a set of tasks and retrofitting it such that it kind of aligns with EDF and RMA. So here the key point is that we modify all our release times and our deadlines such that no task can start before its predecessor, right? So what we do is we basically modify the deadlines and the release times such that a predecessor starts, and only then does task which has a dependency, right? So let's say T1 has to execute first and then T2. So we'll set the arrival time of T2 to be a time after T1. And furthermore, you cannot really preempt your predecessor or even execute before it. The moment we can do that, right, we can basically ensure that our traditional EDF and RMA algorithms will work without being aware of the fact that there are actually relationships between tasks. So this is kind of like a hack. It's kind of like a retrofitting hack. Can work in many cases if this is done properly, but it is quite hard to do this in practice. So the idea here is that we have a conventional task set. We modify the task parameters, which are namely the arrival time, the deadline, then other parameters such that preemption, priorities, and so on. Preemption and execution basically. So once with these, we can then use our EDF and RMA algorithms more or less unmodified, but maybe with some of these additional constraints. So we'll have a slightly modified EDF or RMA scheduler that can take precedence orders into account. All right, so this finishes this discussion on RMA, which is lecture 7. Sorry, this is lecture 8. So now we'll move to lecture 9, where we will discuss some more aspects of clock and event driven scheduling. So now we'll start lecture 9, where we will discuss generalizations of the RMA model. So one of the key points is how do we handle or deal with aperiodic and sporadic tasks. So one of the options could be that we give aperiodic and sporadic tasks either a very high priority or a very low priority, but this of course would depend on the system, right? That what kind of tasks are aperiodic and sporadic, and do they deserve a high priority or a low priority? For example, a burst of sporadic task arrivals can overload the system. Even though RMA does handle transient overloading better, but still many tasks can miss their deadlines if, let's say, we provide a higher priority to sporadic tasks. This will violate the basic premise of RMA. So we can then give them low priorities, but some of these tasks may actually be critical. So we have to develop some methodology to actually deal with such tasks. So there are several techniques, and they are all known as a periodic server based techniques, where we basically create a server task whose job is pretty much to serve a periodic jobs such that it is easier to schedule them. So for sporadic tasks, there are two kinds of sporadic tasks that we were looking at: high priority, emergency events, and non critical ones, which are background jobs. So, this is typically the case when we look at aperiodic and sporadic jobs, they either have a very high priority or they have a very low priority. So, we often do not find them in the middle. So, of course, if background jobs are there, they can be deferred during periods of overload because they are meant to tolerate a long response time anyway. But for high priority tasks, a very obvious way is to handle them by converting them into periodic tasks. So, what we can do is that we can have a periodic server whose job is to periodically run with a high enough frequency to justify its high priority, pick up whatever a periodic tasks have arrived during that time period, and service them. So the basic foreground background scheduling technique, right? So this is again a classic technique, is that aperiodic tasks are executed when there is no periodic task to execute. So this could be a model where you say that, look, my periodic tasks have high priority. They, for example, run with RMS. They are a part of a high priority queue. If they are not there, uh, then of course we create aperiodic tasks which are a low priority queue. All right. So in this case, uh, we will need a separate scheduler for the periodic tasks as and when it runs. So this is like a two-level scheduling algorithm. In the sense, periodic tasks are like the first level, right? If let me call them T1, T2, and so on. And then there is a special task, let's say T4, or let me call it T8, A for a periodic, where the moment this executes, then it starts executing the periodic tasks. So of course, given the fact that this has complete control over them, it can choose any algorithm. So it can choose FIFO, first in, first out, or it can choose EDF, earliest deadline first. This again would depend on the system. So an example over here would be that let's say we schedule these periodic tasks over here, then we would have a whole. Whole means nothing is scheduled. At that point of time, we could maybe use the FIFO algorithm to schedule our aperiodic tasks. Right? As you can see, if a task arrives at this point, then it can be executed in this hole. And if a task arrives at this point, then it can also be executed in this part. Similarly, another task comes, it executes in this hole. This hole means in this gap. All right. So the key idea is that we create a separate periodic task known as an aperiodic server, which in itself is a high priority periodic task. It is created to handle multiple aperiodic tasks. So this is like a two-level scheduler that we have created, which and these aperiodic tasks may have deadlines associated with them. So the period and the execution time is primarily decided based on the characteristics of the aperiodic tasks, right? How to exactly design the system. And furthermore, in a system, we may have one aperiodic server or we may have multiple aperiodic servers in a system. So the system should, in a sense, transparently take care of both. There are various types of aperiodic servers that have been proposed. So we will discuss all of them. We'll discuss static servers as well as dynamic servers. So the aperiodic servers could either be static or dynamic. So among the static servers are the polling server, the deferrable server, priority exchange, and the sporadic server. So we'll discuss all of these. And then we'll go to the Slack Stealer server, which is a dynamic server. So the key idea of the polling server is like this, that if there are no aperiodic tasks at the time that the server is invoked, so it could be, in this case as per RMS. So let's say the server task is invoked and at this point of time, there are no aperiodic tasks. Then the server will suspend itself and it will get invoked at the time of the next period, right? So even if a task arrives at this point of time, too bad. So this is the simplest, and clearly it is easy to implement. And of course, if there are enough aperiodic tasks in an invocation, maximum it will execute up to ES time, right? So up till this time it will execute and then its time quantum will be over. So an example could be like this, that yeah, if let's say the aperiodic server is executing, the task TS, right, in this task set, we have three tasks, two periodic tasks T1 and T2 with ENP 1 and 4 respectively, and for T2, 2 and 6 respectively. So TS is basically the server, and so it has an execution time of 2 and a period of 5. So ideally speaking, the server process, the periodic server, should be scheduled at this point as per RMS. However, given the fact that there is no periodic task to schedule, TS will suspend itself and then again start at point 5. So then, even if a task comes at this point, given the fact that we are polling only when the server is executing, we will wait. The periodic task cannot be executed now. So then it will be executed when the server becomes available, which is this point. And at this point of time, clearly, since there is no other periodic job, there is no conflict. So we can execute the synchronous task over here. Then let's see if another job arrives at this point of time, then of course it will have to wait. Waits till time t equal to 10. The server becomes available and there it can schedule for 2 units. However, A2 needs only one, so it will keep one with it. But given so later on, if let's say another task comes, it again has to wait, which is technically speaking not that fair. But this is the way it is, that this is the simplest algorithm. So at time t equal to 15, again the periodic server is scheduled and then it executes this task, which is this task over here. And this executes over here. This executes over here exactly when the server runs. And again, if something comes here, of course, it's not scheduled. So the key point is to include the periodic server over here, assume some worst case execution statistics, and perform a schedulability test. If the schedulability of periodic tasks decreases, then of course it's a problem, right? Otherwise, there is as such no problem. In this case, the clear issue is that the response time for aperiodic tasks is on the lower side. So the schedulability analysis that we have will basically, it'll just be an additional task. It'll be a periodic task equivalent to the periodic server. So if you see, this is the utilization for all the periodic tasks. This is the utilization, or rather the maximum utilization for the periodic server. And this has to be less than the typical RMS bound. So this is the Liu and Leyland criterion which has been modified for this case. So this again is a sufficient. So let us now do some schedulability analysis. So let us look at the periodic task guarantees. So assume an aperiodic task AI arrived at time RA. It has a computation time which is CA and then it has a deadline which is DA. So the idea is that it may have to wait for some period of time before actually it gets service. So basically how much? So the period is PS and we are looking at a worst case, then it may arrive sometime after 0, which essentially means that at the next period boundary, it may get scheduled. So when it gets scheduled at the next period boundary, then it will execute for some time. So to be on the safer side, the deadline should be after the end of this period. So if you think about it, this would be the entire deadline, which is like this, right? So if we just want to be on the safer side and we want to ensure that a deadline is never missed, so what is a sufficient condition? So a sufficient condition is basically that in the worst case, RA could be as close to the 0 as possible. Then it means that it will be scheduled over here, which is the next time the period starts. If CA is less than equal to CS, then it means that within that epoch itself, right, within that cycle itself, the work will finish. But technically speaking, this can go right till the end of the period over here. And then the deadline can be over here. So basically the maximum time that we are talking about between, let's say, the start and the deadline, that in a sense upper bounds 2 times PS, right? Because one PS is fully going here and another PS is fully going here. So that in a sense upper bounds it. So we can say that 2 PS should be less than equal to DA, and that is a sufficient condition for a periodic scheduling, subject to the fact again that we can execute our periodic jobs at the beginning of the next cycle, and priority wise this is allowed. So the response time, let's say with an arbitrary computation time, would basically become TS. Oops, sorry, this should be PS over here. So basically we wait for the first period, right? So we wait for the first period because the execution would not have started. After that, what we do is that let's say if the job requires EA time units and let's say the maximum we can provide per cycle is ES, then we need these many cycles. So this is exactly what this expression is conveying. We multiply this with the cycle time, which is PS. So this is the total response time of the job, which should be less than equal to the deadline. This completion time may prove to be too long for many applications. That is why the next improvement for an aperiodic server is known as the deferrable server. The key idea with the deferrable server is it is similar to a polling server, where the server runs periodically with a very high priority. So again, when there are no outstanding aperiodic tasks, the server will, in this case, it will not actually, just ignore the task and just move on. Instead, what it's going to do is actually defer its execution. So we will see what that means. Then when an aperiodic task arrives, the server will actually start executing it instead of ignoring it, and it will again maintain its priority. We'll again see what this means, right? So the words that you need to remember at this point of time are the words defer and maintain its priority. So these will be defined in the subsequent slides. So the key idea of a deferrable server is that every server will have a computation time, which is basically the time that it can execute within a given period. So we have been calling this with different names, ES and so on. So this is replenished at the start of its period. And let's say if we execute for this period of time, it becomes 0. Again, it gets replenished at the start of the next period. So as opposed to the polling server, at least our aim or declared aim is to provide a better response time for aperiodic tasks. In the sense, our feeling with the polling server or our biggest uh, issue with the polling server is that it was taking a lot of time. So let us look at an example. So let us look at 3 tasks. So the first task is 1 4, execution time of 1, period 4, execution time of 2 and period 6, and then of course the server process, which is execution time of 2 and period of 5, right? 4, 5 and 6. So this is task 1 for you, right? As you can see, 1 unit. This is task 2 for you. So as you can see, it needs 2 units of time within 6. So basically it's this and this. In this case, it's both together. In this case, it's both together, right? So this is the execution of T2. Now let us look at the execution of TS, which is an aperiodic task. So the server at this point, so let's say will defer its capacity to handle any future aperiodic task. So let's see how it will do that. So let us say a task arrives here with a demand for 2 time units and it's aperiodic. Here we will differ from the polling server in the sense we will not need to wait till time t equal to 5. So we don't have to wait till time t equal to 5. In fact, this is exactly what was causing the slow response time in the polling server. Instead, what we do is we execute it immediately. All right, because nothing else is executing. So in the typical preemptible RMA EDF style, we execute it immediately. Then let's say we go to the next period, where again another task arrives at period 1. Well, no problem. Don't need to wait till time t equal to 10. The moment task T1 ends, which is at this point in time, we execute A2 immediately. So why is A2 not scheduled at time t equal to 8? Well, because this task is executing. That's why. Right. So and furthermore, the task T1 is higher priority than TS because this period is 4 and TS's period is 5. Let us now look at the priority exchange server. So this is similar in many ways to the polling and deferrable servers. So recall that in a polling server, we wait till the next interrupt. If there is an aperiodic task, we execute. Otherwise, if something happens in the middle, we don't care. In the case of a deferrable server, what happens is that we have these periodic interrupts But the point is that, of course, at a periodic interrupt, if we have a task, we'll execute it. But let's say even otherwise, the budget doesn't drain. So as is the case in polling, if something comes at the middle, we ignore. In the case of a deferrable server, we actually don't ignore. If you would go back to our example, so what we would do is that if a task comes, for example, we had this over here, that in this case a task did arrive. The moment a task arrived, we were able to execute it immediately over here. This is something that was not there. But then, of course, if another task arrived here, our budget got exhausted because our budget in this case is 2 units. So if the budget gets exhausted in a period, of course, then we can't do it. And then let's say if another task arrived here, we kept the budget which was replenished at t equal to 5. So in a sense, the reason this is called a deferrable server is because it defers the execution of a task to when a task is available and adequate budget is there. So in this case, what happened is that adequate budget was there because it got replenished to 2 over here. And the moment a new task came, we waited for the processor to be free. And at this point of time, we executed A2. In a certain sense, the deferrable server defers the budget of the task, where the budget is defined as the amount of runtime that can be expended to execute a task. So this is something that we have seen. So the deferrable server is basically something, it's more of a common sense kind of thing that whenever there is a task, we actually execute it. And so this ensures that a lot of the slack is taken up by executing aperiodic tasks. Now let's look at a priority exchange server. So here the idea is that if there is no aperiodic task, which is when the server is running, then the high priority server, so the server in this case has a high priority, this would exchange its priority with a much lower priority periodic task, right? This does not happen indefinitely, it happens for a period CS dash, where this is the remaining computation time of the server. So the idea is quite simple that let's say the server, similar to a deferrable server, it maintains a budget. So let's assume its budget is 5 per cycle. And let's say 2 out of this have been exhausted. So the existing budget is actually 3 time units. So what it does is that since it has the budget for 3 time units and it sees that there is no aperiodic task in sight, and given the fact that it can execute and it is known to be a high priority process, it will kind of exchange the priority, in the sense it will become low priority and it will give its priority to another task, another periodic task, such that it can execute for this budget interval, which is 3 units. So then how will this actually work out? So the way that this will actually work out is like this. So this basically means that the priority in an interval, so in between two interrupts, the priority of the periodic server goes down. So its computational time is still maintained, right? But the point is that its priority, of course, will go down once its priority is exchanged, right? So that is, that's the key part of this idea. But the moment that the next interval begins, its computation time is replenished, its budget is replenished. So in this case, the key idea is that you sort of want to give more priority to periodic tasks. So aperiodic tasks get a low preference for execution or a lower preference for execution. So basically, this is like, one of those compromise formulae where the idea is that, look, you have done your part, you have some budget left, give your priority to us and your budget to us, of course, and we will execute for that time. So this is not really, doesn't favor aperiodic tasks the same way that a deferrable server used to. Hence, it offers worse response times. But the idea is that for a periodic task set, of course, it is better. So it's better for periodic at the cost of aperiodic. Hence, it has better schedulability bounds and in many cases a better performance also. An example of a priority exchange server. So let's say at this point of time, an aperiodic task exists to utilize the server capacity. All right. So basically, we realize that there is no aperiodic task to utilize the server capacity. Then a much lower priority periodic task TL, so L for low and TH for T high and S for server. So TL starts to execute at the server's priority. All right. So that is the most important part, that it starts to execute at the server's priority for CS minus E time units, where the color of the box indicates the priority. After that, TL starts executing at its own priority once the budget of the server is over. So once it's over, it will execute at the yellow priority, which is a lower priority, as opposed to the preceding period, the preceding time frame, where it was executing for CS minus E time units at the priority of the server. So then what happens is, given the fact that if there are periodic tasks to serve, given the fact that the priorities have been exchanged, the server will also execute for a maximum of CS minus E time units, right? But mind you, this execution that is happening with the yellow priority level, which is a lower priority level because the priorities have been exchanged. So some notes regarding the schedulability analysis of the server. So what can be seen intuitively or informally is that it improves the schedulability of the periodic tasks. The exact work that is done is much more complex. So of course, because the priority changes dynamically, that is why coming up with an exact relationship regarding the schedulability is harder. So now let's come to the sporadic server. So the sporadic server uh, improves the response time for aperiodic tasks. So what have we seen up till now? We have seen the polling server, which for aperiodic was very bad. Then we looked at the deferrable server, which was always in an I want to serve you mode for aperiodic tasks. Then we looked at the priority exchange server, which I would say was somewhere in the middle, in the sense that it was, well, mostly bad, but also somewhat good in the sense that it still allowed a periodic task to execute at a lower priority. So it is somewhere in the middle of polling and deferrable. So the sporadic server that we will discuss doesn't degrade the utilization bound for the periodic task set, and this has been incorporated into the POSIX standard. So the key idea is that it uses a different replenishment policy as opposed to the ones that we have seen. What it does is that it replenishes the execution time, or what we have been calling the budget of the aperiodic server, only after one full period has elapsed after the start of execution of an aperiodic task. In the sense that if an aperiodic task executes, it waits for a full period and then only replenishes the budget, as opposed to doing that at fixed boundaries. So the replenishment rule is like this, that it compensates for the deferment in the sense that let's say that we are executing a task. So then, in the case of a deferred scheduler, what would happen is that if, let's say, these were the points at which the interrupt comes, the moment we execute an aperiodic task, it will get replenished over here. So this is the replenishment point, RP. But in this case, what we do is that we actually wait for one full period, right? And we do not. So this is that's the reason for aperiodic task is slightly worse than the deferred scheduler. In the sense, we don't replenish it over here, but we replenish it at this point. So in a certain sense, it is not a full deferment, but somewhat of a reduced deferment. So just to give an example, so let us look at three tasks where the server has the highest priority, 2, 8. So the first one is 3, 10, 3 units of computation, 10 period, 4 units of computation, 15 period. So as we can see, we have scheduled T1 and T2. So now let us schedule the aperiodic tasks. So at the beginning, there is no aperiodic task, so the server will defer its capacity, quite like the deferrable scheduler. The moment an aperiodic task comes here and it wants 2 units of time, we can schedule it right away, quite like the deferrable scheduler. So once this is scheduled, we will finish the budget, right? So basically, our budget was 2, and our entire budget got exhausted over here. So then let's say task arrives at 7, but at this point, the server does not have any capacity. So the capacity will get replenished 8 units after 2. So 2 plus 8 is equal to 10, which means the capacity will get replenished at this point. At this point, server has the capacity to schedule A2 and it does. So let me again go back to this point. So at this point, the capacity gets replenished and A2 gets scheduled. All right. So the key point is that we are not as bad as priority exchange possibly because we are not reducing the priority of the server, but we are not also replenishing it at immediately the next boundary, but we are replenishing it after some time. So basically the moment you start execution, so after some time, which will be this point, we are replenishing. So it's kind of trying to strike a compromise between deferrable and fixed priority. So the sporadic server with this design decision has made its way to standards as well as to many, many implementations. Now coming to the dynamic server, so if we look at the response time of the polling, deferrable and sporadic servers, it does offer improvements in terms of response time. So here the idea is we do not create a separate periodic task. Instead, what we do is we create a passive task which basically steals processing times from periodic tasks. So periodic tasks remain as is, as they are. So we create a small task which is quite intelligent. So this will, of course, this has given the fact that it is dynamic, it has more overheads. But given the fact that it can see the execution, it can steal time from other periodic tasks and then it can execute a periodic jobs without causing any deadlines to be missed, right? So this guarantee is a hard guarantee for periodic tasks and kind of a soft guarantee for aperiodic tasks. So this is known as slack stealing, where slack is basically where there is some time in which we are not executing. So in this lecture, we have seen a lot of things. So we basically have finished our discussion on EDF and RMA. So of course, we did start our journey with a table-driven approach, right? Which was essentially a part of clock-based scheduling. So we looked at table-driven approaches and cyclic schedulers. Then we moved to event-driven schedulers. So in event-driven, we saw that EDF and RMA pretty much cover the entire space. EDF for dynamic priorities and RMA for static priorities. And then we discussed a bunch of extensions and special cases. So for example, RMA supports these many kinds of servers, which again can be static servers for a periodic task assignment, and or they could be dynamic servers for again a periodic task assignments. So after this, what we will look at is that we will look at situations where there is a resource dependency between tasks, in the sense that two tasks cannot run if they need to acquire the same resource. One task needs to run and finish and then the next. So this will create very unique problems such as deadlocks and so on. So that will be the topic of our discussion for the next few lectures.